All right, once you get down naming, then we can move into conformations and looking at different molecules. Newman projections are the best way to observe a single bond rotation. Now, if you have your molecule kit, the best thing that we can do, and we'll play with one in class, and I'll hopefully have shown you before this how to make your own if you want it, or which ones to purchase if you have to purchase. But single bonds can rotate. That's because they are a direct overlap of an atomic orbital that has the ability to rotate around the axis in the middle. And so there are multiple 3D shapes that we call conformations. A conformation is just being able to rotate a structure to move some bonds around. It's the same molecule, it's just looking at it in a couple of different ways. So a Newman projection is going to be the best way that we are able to actually observe the rotation around a sigma bond. And these are going to be mainly for alkanes that are acyclic, not in a ring. Now, we maybe have done a lot of wedge and dash ideas, right? Or skeletal structures. And that's great. Wedges and dashes showing the tetrahedral is awesome. There is something called the sawhorse, where just imagine starting to rotate around here so that we can start to view that center axis a little bit differently. It's like taking your sigma bond, this one right here, and starting to look down the sigma bond, not head on at the sigma bond like the wedge and dash. A Newman projection is when it's like we're a little stick person over here. There's me. And I'm looking down the sigma bond where there's one carbon in the front, that red carbon, and there's a carbon in the back, and that's going to be this carbon with the blue hydrogens. And so Newman projections are ideal for comparing the relative stabilities of specific conformations of a molecule. When we're looking at a Newman projection, we will be looking down one bond at a time, a specific carbon-carbon bond. So there's the disembodied eyeball right here. Ooh, scary. And it's looking down this bond right here. And so what we want to be able to do is draw the carbon in the front. And what does it look like? It has some hydrogens that are wedged and dashed on the top and one that's coming straight down. So let's draw that first. What that person or what that little eyeball sees is this front carbon. I'll just label it F. It's got a hydrogen in the front, on the two on the top and one on the bottom. Now the back carbon here has a hydrogen sticking straight up, and then the wedge and the dash hydrogens below. To draw the back carbon, we do a circle so that we can say, hey, here's the back. That's what is happening. That right up a little bit. Hydrogen sticking straight up and two hydrogens out to the side. This is a Newman projection. We have a front carbon and a back carbon, and we are visualizing the sigma bond that's in between this bond right here down the middle. And what we're really focused on is seeing how much space is in between the groups on each of those carbons. So looking at this, not necessarily of the bond itself, but how does the bond rotate the groups around it? So we're going to start off with very simple structures. We'll get into a little bit more complex things. But first, what we want to do is just be able to take a molecule and draw. This should be a chlorine. There. So I like to, at this point, draw in the hydrogens. If this is my little disembodied eyeball that's looking down this bond, I have hydrogens here and here, and I have one here as well. I like to note that because when we're looking at this, these hydrogens that are wedged are going off to the little eyeball's right-hand side. Pick yourself up and put yourself right where that little eyeball is and say, okay, if I have hydrogens coming out of the paper or out of my screen, that would be on the right-hand side of that little eyeball. The dashed CH3 and dashed H are going back into the screen, behind the screen, or behind whatever you're watching this on, and that is to the left of the eyeball. And then we also have this methyl and this chlorine, which should be opposite of each other. One's on top and one's on bottom. So drawing that front carbon and back carbon. Front carbon first. We have the Y. There's the front. There's two hydrogens. I'm going to color them how we had colored before. The right hydrogen and the left hydrogen. And what's down at the bottom? A CH3 group. I'm going to write in the CH3 just so that we can see it. Okay, front carbon, done. Back carbon, do the circle. Now we have a chlorine that's sticking straight up. That chlorine should be on the opposite side of my methyl group, and it is. Excellent. And he has two other groups. Hydrogen is wedged coming out towards him. Methyl is dashed. What's important about a Newman projection is you write everything attached. Do not leave off groups. Do not just write C's. Do not just write H's. Do not just leave them blank. Write everything that's attached to each of those atoms. So this is how we would write a Newman projection given a specific orientation, right? So when we're looking at this guy, specifically down this bond, that is what we see. Try building it if you have a molecule kit and putting your eyeballs down the same path as this picture. A conformational analysis is really helpful to do when we are diving into Newman projections. The angle between atoms on adjacent carbons, so you're looking down a front and a back carbon, those are adjacent carbon atoms. And so the angle right there between those, the front hydrogens and the back hydrogens is called a dihedral angle or a torsional angle. It is 60 degrees on the molecule below. If we have a full piece of the pie that is 360 degrees, and we divide it into 6 pieces, that's 60 degrees. So each one of these is 60, 60, 60, 60, 60, 60, 60. Excellent. So as we're looking at that dihedral angle, what's important to note is that I can rotate one of the carbons, either the front or the back. Dealer's choice, it doesn't matter. In your textbook, I believe they tend to rotate the front carbon. But again, pick one and rotate it. What happens when you rotate 60 degrees? What you are doing is you are turning one part of the sigma bond, rotating it along the axis of the sigma bond, which has free rotation. You can turn that all around and around and around like a little merry-go-round. We're going to turn at 60 degrees at a time until we reach the full 360 circle and get back to the beginning. The reason why we want to do this is because we see two different conformations now. We see a staggered and we see eclipsed. Staggered meaning that each hydrogen has space. We're kind of peekabooing. Here's the front ones, and the back are peekabooing in between. Eclipsed is exactly what it entails, the idea that we are hovering one hydrogen over the other. Now, staggered is lower in energy than eclipsed. The reason for this, main reason, is because of something called hyperconjugation, which we'll get to in just a little bit, but also the idea that there is more distance in between the hydrogens when they are staggered versus when they're eclipsing. They're bumping into each other. Electrons repel. And that increase of energy is what we call torsional strain here. It's the difference in energy between these two conformations. So when we go from staggered to eclipse, there is a difference in energy of 12 kilojoules per mole. And so we can look at that difference in energy and start to plot out the energy diagram of rotating. Now notice that we're starting here with the hydrogens on opposite sides. And as we start to rotate the front carbon, we rotate 60 degrees. We go from staggered up to eclipse, 12 kilojoules of energy, higher in energy. And then we'll rotate again back down to staggered. And notice how I've got those two hydrogens closer together. The bottom or the back carbon and the bottom hydrogen are not moving. The only thing that's moving is the front carbon. So that red hydrogen in the front is what we're trying to keep our eyes on. Each one of these staggered and eclipsed conformations is identical. Every 60 degrees rotation, we flip from staggered to eclipse, back to staggered, up to eclipse, back to staggered. And the difference between staggered and eclipsed is 12 kilojoules of energy. What that means in reality is it's possible that the eclipse conformation is 12 kilojoules less stable because of these two hydrogens and these two hydrogens and these two. The electrons in those bonds are closer together. So if the total cost is 12, that must mean each hydrogen costs 4 kilojoules per mole. There's 3 of them altogether, 3 eclipsing groups, and so 12 divided by 3 is 4. So eclipsing CH bonds, a CH bond on the front and a CH bond on the back, costs 4 kilojoules per mole. Excellent. So with this difference of 12 kilojoules per mole in stability, at room temperature, 99% of the molecules will be staggered. The molecules don't like to rotate because it costs energy. It can rotate, especially if we heat things up or if we start a reaction. It can rotate for sure. But what's important is that it does cost energy. So another reason why this is important is the idea of hyperconjugation. Now, when we are staggered, notice this is back to our wedge and dash format. When we are staggered, when we have bonds that are opposites of each other, looking at a staggered position, why is staggered so much more stable? Partly because eclipsed positions have electrons that are closer together, electrons in 2 separate bonds. Eclipsing costs energy because of electron repulsion. Excellent. The other reason is because in staggered, we have something called hyperconjugation. Hyperconjugation is the idea that in a stabilizing interaction, a filled bonding orbital is parallel to an empty antibonding orbital, or empty orbital in general. And so when we're looking at this diagram, notice that there's an overlap here. Now this is filled. There are 2 electrons here. This one is empty. And it's also antibonding. It's high in energy. These electrons in the filled bonding MO, the sigma bond between carbon and hydrogen on one side, is able to actually push some electron density into the antibonding orbital. Now the antibonding orbital is for this carbon-hydrogen bond right here, down here. This empty orbital is the space of antibonding that is empty. Remember when we talked about MO theory, for every sigma bond, there is a sigma star, and that sigma star should be empty. And right here, we can utilize that emptiness to spread out some of the electron density from another filled sigma bond. That hyperconjugation does not exist in the eclipsed format. Let's move up a little bit to propane real quick. Propane, our 3-carbon chain. So now what we see is we have a methyl group that we're trying to locate around as it rotates 60 degrees. Again, the only difference here between ethane and propane is 14 kilojoules per mole instead of what we saw before, which was 12. And so the big difference here is the barrier to rotate for propane being 14 means that there's a little bit something else going on. We know that a CH costs 4 kilojoules per mole. This one, 4 kilojoules per mole. So how much does this one cost? Well, 14 minus 4 minus 4 is 6 kilojoules per mole left over. So an eclipsed CH3 with H is 6 kilojoules per mole. Costs a little bit more. Why? Well, a methyl group is bigger than a hydrogen. There's more electrons. There's 3 more bonds in that CH3 group. And so when we're looking at that, the HH eclipsing costs 4, but the CH3 to H eclipsing costs a little bit more because we're getting bigger atoms. And so we can start looking at a rotation, looking at a structure and being able to analyze that torsional strain and the cost for rotation of individual groups that are eclipsing. Again, remember, most often, not always, most often we do these calculations for eclipsed groups. Okay, let's go to butane, 4 carbons. Now again, we can see a couple of different things here. When the 2 methyl groups are spread out, we're looking down the carbon 2 to carbon 3 bond right there in this conformational analysis. If we were to look down that bond, that's where our eyeball is. We see 2 different actual values here. When the methyl groups are opposite of each other, that is the lowest energy possible. This is actually called our anti-configuration, when the 2 biggest groups are farthest apart. They're on opposite sides. And notice if we rotate 60 degrees, we get an eclipse position that is 16 kilojoules per mole higher. That makes a little sense. We have 4, 6, and 6 for our cost of energy, right? 4 for the eclipsing hydrogens and 6 for each of the methyls eclipsing a hydrogen. And then when we rotate again, notice we're not at a lowest energy conformation. It is staggered, but it's staggered and it's called gauche because it's not the best. The methyl groups are actually still close together. And this is where a staggered position costs energy. It costs 3.8 kilojoules per mole. We'll talk about that in our chart at the very end, but what's important to note here is that even in a staggered conformation, you can have groups bumping into each other, and pushing those big groups together into this gauche staggered position is difficult for it. Rotate again and we get our the worst or the highest energy position, which has the eclipsing methyl groups. This should be a lot of energy looking right there. We'll calculate that in just a second. 19 kilojoules per mole higher than our anti-staggered. We get another gauche where the 2 methyl groups are still staggered but next to each other. And again, still 3.8 kilojoules here. Rotate again, we get our same 16 kilojoules difference in the eclipse, and then back down to our anti-staggered, which is the lowest energy conformation. Now, the stability difference between, let's just draw our anti and our gauche. Here's our anti, big groups opposite of each other. And I'll draw one gauche. And here is where there's some steric hindrance, there's some bumping into each other. And that is what costs 3.8 kilojoules per mole. And it costs that because those methyl groups are actually interacting. They're close enough that we can cause a little bit of what we call steric strain, higher energy, because the two big groups with a lot of bonds with more electrons, those electrons are closer together, and we know electrons repel. What about our highest energy conformation here? If we see these eclipsing groups, we know hydrogen's eclipse at a cost of 4 kilojoules per mole. The total was 19, so minus those two fours, 11 kilojoules per mole for two methyls eclipsing. These numbers you do need to know. This chart right here is what I want you to know. The energy costs for eclipsing and gauche interactions can be used to give the approximate energy of a given conformation. We'll practice that a lot in class. Being able to draw the given conformation like we did last time, and then being able to analyze the eclipse position and the cost of it will be an important idea on your exam.